The very first thing we're going to do when we look at some of the voltages from the Xiao module is set it up in the solderless breadboard. Remember, we said, gosh, one of the limitations is we only have the one ground pin right here. So we're going to make the most of it. First thing we're going to do is we're going to use the standard convention of the inside rails are going to be ground on both sides. So we're going to connect the ground pin to the inside rail here, and then we're going to strap this over to the other side and get it to the inside rail over on this side. And that way we'll be able to use the spring ground probe in the 10x probes pretty easily when we look at some of the signals. Now, to do that, again, we want to use best practices for the solderless breadboard, which means short wires and color-coded. And so for ground, we're going to use black. So grab a strip of black wire, and then don't be intimidated or hesitate to make your own short wires. So we're going to take about quarter to half an inch length off the end. First one we're going to do is go from the ground pin to the inside ground, and so something on the order of this length. So we get a short length. You hold it tight in the middle. You grab it a little bit from the edge. You push down, not so hard to cut, but hard enough to make an indentation in the plastic. You rip it off, and now we've got our little wire, and this is going to go between the second pin here, which is ground, and the inside track. So now we've connected the Xiao module ground, which is the USB ground, into the inside column. And then we're going to strap across, so we get another black wire, and we're going to go roughly like that. So I think something, maybe about like this ought to do it for us. And so again, we're going to be making a lot of these wires, so get in the habit of doing it. You make an indentation. You can see here the indentation. You grab it, and you just strip off the tip. Do the same thing to the other end. And now we're ready. And this is going to go from the ground pin over to the inside column on the other side. And we're done. And we still have easy access to the other pins along the side. First step. Now we can take a look at some of the voltages that are there. We've got, after all, 5 volts in the first pin, and we have 3.3 in the next one over. So just to check those voltages, it's plugged into USB. There's a power light is on. We're going to connect ground. Again, we're using color coding here for the multimeter. Ground is going to go anywhere on the inside rail. We'll put it over here to get out of the way. And this pin over here is going to be 5 volts. Let's see. Hey, there it is. 5.6 volts. Now, the USB hub that is plugged in my computer, the spec is actually plus or minus 10%. So the fact that we're just slightly over 1% is great. That says, boy, really good, accurate hub. The accuracy of the DMM better than a percent. I'd rate it, I think the actual rating is 0.5%. I've calibrated these or validated them against other high performance multimeters, and the absolute accuracy is actually within about 0.1%. So that's 5 volts. So that's pretty good. Let's take a look at the 3.3 volt. And the 3.3 volt is provided by an onboard regulator on the Xiao module. This is an LDO regulator, and the rated accuracy is about 1%. And look at that, we get 3.28. Now, I thought it would be 3.3, but it's 3.28. So we're off by 20 millivolts. 20 millivolts out of 3 volts. That's less than 1%. So we're within 1% absolute accuracy, well within the specification. Remember this number, 3.28, because we're going to use that as our reference. Now, whenever you have a power source, always useful to know what's the Thevenin output resistance of it. And again, we know a really simple way of measuring that, because effectively what we're doing is we're modeling the power source as, here's the Thevenin voltage, there's a Thevenin output resistance, and this is the pin that we see coming out. what we're measuring, because it's unloaded in this case, is the Thevenin voltage. So for the 3.8 volt rail, for example, we measured 3.28 volts, and that's the Thevenin voltage. And what's the Thevenin resistance? Well, the way we tell is we add a load. And I'm going to add a 100 ohm resistor here. Now, if I just put 100 ohms across here and it's 3.8 volts, the current is going to be about, this is the V over R. Let's see, the voltage is 3.3 over 100 ohms. So we're talking about 33 milliamps. Not so much. I don't think we're going to break the 3 volt rail if we add a 100 ohm resistor. And by looking at that difference, so the Thevenin resistance here, that Thevenin resistance is going to be the voltage drop across it when I add the 100 ohm resistor divided by the current. And what's the current? It's the voltage that I measure, so it's the voltage change that I measure here after I add the 100 ohm resistor divided by the current, which is the voltage measured loaded divided by 100 ohms. We pull it up here and it's over here. And so we can get the Thevenin resistance pretty easily. So let's grab a 100 ohm resistor. So we have our stack of resistors here, and here is a 100 ohm resistor. Let's see. And the one right over here, this is 100 ohms. And we're going to measure, we've got the voltage. Here's the voltage unloaded, 3.281 volts. Now we're going to add a 100 ohm resistor across that the 3.3 volt rail to ground. We're going to measure the change in voltage. So let's connect that in. Here's a 100 ohm resistor. Now before we do that, always again, important to calculate the power. What's the power going to be? Well, the power is V squared over R. So let's see, so that's basically 3 squared is basically 10 divided by 100. That's 0.1 watt. Okay, so these are a quarter watt rated. So we're under a quarter watt. You know, maybe it might get slightly warm, but that's about it. So let's do this. Let me show you the voltage. There it is, the unloaded voltage. Now that's the Thevenin voltage. Now I'm going to put that resistor across there. And did you see the voltage change? Let me do it again. Let me take it out. So we're at 3.28. Let me put it in. So we're loading it down. 3.27. We had a drop of about 10 millivolts. So now we can figure out what is the loaded resistance. We can figure out what is the Thevenin resistance. The Thevenin resistance is the voltage change, 10 millivolts, divided by the voltage I measure, 3.27, times the 100 ohms. And what's that? Well, we can just kind of roughly estimate it. Let's see, this is, you add 100 here, this is about 1 over 3. That's about 0.3 ohms. That is spectacular. That's 0.3 ohms. And that's because of the really good LED on the board. That says that, gee, you know, through normal operation of the core and as we add things to it, we're probably not going to see much change in that output voltage. But don't count it as a very good reference because, you know, it's got 0.3 ohms, and even if we got a 10, 20 milliamps of current draw through it, we're looking at 10 millivolts of voltage drop, and 10 out of 3 is about it's still less than 1%. So really good number to remember. And is the resistor warm? Nah, I can't feel any heat from it. Okay, now we're ready to drive the DAC and look at the ADC.